Hello everyone, welcome back to Foolish Engineer. An analog front end is the sensing ears and eyes of a BMS, a dedicated chip that measures cell voltages, current, and temperature with high precision. It's used in BMS to reliably monitor and protect every battery cell, ensuring safety, balance, and performance even in low voltage packs. Stay tuned to go more deeper into this. Let's imagine we are working on a project, say designing a battery management system product, with enclosure and all. Sounds simple, right? Until we have component delays, board fitting issues, thermal problems, or safety compliance. That's where Altium Develop saves the day. In this, we can capture all the requirements in one environment so everyone sees them. Then, its BOM portal helps to check the selected component availability, pricing, and life cycle status. For traditional schematic and PCB design, Altium Designer is already there. But the Altium Develop helps with MCAD ECAD code design for mechanical engineers to check the PCB fitting. When the design is done, we get a platform where team members review and give feedback on contexts like safety and pin maps, etc. After review is done, Altium Develop generates release packages with up-to-date BOM and design documents, and it preserves version history so we know who approved what and when. Finally, Altium Develop saves all of the data like version history to evolve the product during production. Our life gets easier with Altium Develop. It is faster, safer, and smarter. If you want to develop a full electronics product, you can check the link in the description to know more about it. We are continuing our battery management system series, so if you haven't seen our earlier videos covering BMS basics, MOSFET switches, current sensing, be sure to check those out as well. Now, let's see what is an analog front end, or AFE for short. It is also called a BMS IC. Let's understand by the help of an analogy. I guess we have all attended school, where as a student, we sit in a classroom, the class teacher teaches and monitors us. But we also used to have that snitch class monitor who boasts all our secret to class teacher and runs behind him. Now imagine this battery management system is like a classroom. A microcontroller is the class teacher, which is the main brain who keeps everything safe and running smoothly. The cells present in the battery pack are the students in this class. No matter how smart a microcontroller is, even the smartest brain needs eyes and ears in each corner. So the analog front end, or a BMS IC, is like that classroom assistant or a class monitor who keeps track of each student or each cell in BMS and immediately reports if someone is causing any trouble. In other words, it's an electronic circuit, often a dedicated chip, that sits right next to our battery cells and measures everything important: cell voltages, pack current, temperatures, you name it. The AFE takes all these tiny analog signals and amplifies, filters, and converts them into digital data that the BMS's brain can understand. It's a special monitoring chip with multiple channels that watch over the battery's health, kind of like having a mini multimeter on every cell. The AFE is a frontline sensor and safety interface between the battery cells and rest of the BMS. It reports cells' health status to keep the battery safe and happy. And as we'll see, a well-designed AFE is critical for battery safety and performance. You might think I've only got 24 volts or 48 volt battery pack. Do I really need a fancy AFE chip? The answer is yes. Even low voltage packs benefit big time from an AFE. It's like asking if a small car needs a dashboard or a seat belts. Of course, it does. Just because the pack's voltage is lower doesn't mean it can slack off on safety and monitoring. Low voltage systems like 48-volt batteries in scooters, e-bikes still can overcharge, overheat, or get out of balance. An AFI is the watchdog that monitors all these cells and makes sure nothing goes boom. In fact, for low voltage BMS, AFIs are often optimized to be simple and cost effective, but highly accurate for measuring voltages and shunt currents. Using an AFI in these systems simplifies the design and boosts safety. There are multiple AFIs that are specifically made for up to 3 cells or 15 cell battery packs, perfect for things like power tools, typically for 18-volt pack, through e-bikes of 48-volt system. Instead of tangle of discrete components, one of these AFI chips provide one-stop solution. It can measure all cell voltages, monitor pack current, temperature, drive cell balancing circuit, and handle over or under voltage protection, all in one go. This not just optimizes PCB space and reduces cost, but also gives level of precision, reliability, and that's hard to get otherwise. Now you might ask, can I just use bunch of ADC inputs on a microcontroller or few comparators to monitor the cells? Do I really need a dedicated chip? Well, that's a fair question, and it gets to heart of what makes an AFI really special. In theory, we could piece together discrete components, an ADC for each cell, some op-amps to scale up the voltages, comparators to trip on dangerous levels, and isolation amplifiers if needed. But an AFI's purpose is to build for battery monitoring. It's like Swiss Army knife with all those tools integrated and optimized to work together. This brings a few big advantages. AFIs use high-resolution ADCs with precision high-voltage references, tuned for measuring cell voltages with millivolt levels. They often include self-checks and are designed to give consistent, trustworthy readings over time. Many ICs can handle high common mode voltages for a multi-cell stack and provide isolation or safe interfacing to the MCU. A single AFI chip can often be configured for different number of cells or chemistry, whereas using discrete solution might need redesigning of each case. Another way to see it, a plate ADC will tell us a voltage number, and a comparator will tell us over threshold or not. But an AFI will manage the whole measurement process. It will amplify tiny signals, filter noise, convert analog data to digital, maybe even do some initial analysis, and communicate the data in a robust way to the controller. It's designed to handle the nasties of a battery environment. Things like voltage spikes, noise from a motor, and even failure conditions like wire coming loose. Some AFIs can detect an open connection to a cell. In short, using an AFI is like hiring a professional battery nanny, whereas using discrete ADCs is like trying to DIY with many separate baby monitors. It can work, but it is prone to error and it's a lot of extra effort. From a design perspective, AFIs also save a lot of time. They come up with datasheets telling us exactly how to hook up cells, what accuracy to expect, and often have built-in protections like shutting down charging if any cell overcharges, independent of the MCU. So, while in principle we could build a BMS analog frontend from the scratch, but in practice, using a dedicated AFI IC is a no-brainer for anything beyond the simplest systems. It's more precise, safer, and ultimately cheaper when we factor in the design time and component count. That's what makes AFIs so special compared to the generic ADCs or comparators. They are the specialized multi-tool for this job. Now let's pop open the hood on the AFEs itself. Inside an AFE, it's like a mini lab dedicated to battery. There are multiple sensing circuits and helpers working together. Typically, an AFE has voltage sensing inputs for each cell. Also, temperature sensor inputs from thermistors or sensors on cells. Amplifiers to boost tiny signals, filters to clean out noise, and ADCs to turn those analog readings into digital numbers, which provides data to the MCU over some communication interface like SPI or I2C. So it has all the special circuits inside. One group continuously checks voltage like voltage inspector, and another monitors temperatures. All these measurements get amplified and calibrated, which is precise down to millivolt level. Then, these analog signals hand over the data to the ADC department, which converts this value into digital signals with high precision. Many BMS ICs use 12-bit, 14-bit, even 16-bit ADCs for fine resolution. Finally, this data is packaged and sent to the microcontroller. The BMS ICs also include cell balancing circuitry, especially for multi-cell packs. So AFE is not just a passive observer, but also a part-time mechanic. If one cell in series is overcharged, the AFE can turn on bleed resistor to gently drain it, using a set of small transistors or FETs, keeping all cells balanced. In low voltage battery packs, say 4 cells, the AFE can often directly interface without special isolation, which simplifies the things. In summary, the AFE is a mini analog measurement system. Multiplexers plus ADCs, precise reference, protection circuits, balancing circuit, and communications interface, all optimized to work together to give us accurate readings with minimal fuss. Pretty neat, right? And that's the beauty of an AFE. It's the silent guardian that keeps our battery pack in line by measuring, protecting, and balancing every cell so nothing blows up. In the next video, we'll uncover how to deal with different types of batteries and the practical design challenges. If you found this video useful, give it a thumbs up and hit subscribe button. And stay tuned for more exciting content.